Yes, and Ariba indeed, and welcome. But now, I'd already replaced the original instruments on my TR7 with individual units. However, the fuel gauge was still the original, although I'd fitted the works into an old oil gauge to make it look like the rest of the gauges. Now I wanted to try and make a new gauge with a 270-degree movement of the needle. The project's going to use a tiny stepper motor designed for use in instruments in cars and available very cheaply on eBay, together with an Adafruit Trinket, which is a tiny microprocessor programmed like an Arduino. It's going to be fitted into an old oil gauge, so let's start. Gently opening up all the way around, bit by bit, with a screwdriver. Then you just pop the bezel off and get at the inside. Gently prise off the needle. And undo the screws. An interesting board and gauge mechanism, but you can just discard this. Take a thin piece of Tufnol or similar plastic. There's a little tube of plastic just round the spindle for the needle, and the hole in the Tufnol needs to be a snug fit for this. Now to drill the holes for the fixing screws. Enlarge the hole for the cable. Now we need to fix the wires onto the terminals on the stepper motor unit. Soldering would damage the unit, so I'm going to use wire wrapping. Wire wrapping used to be all the rage at one time for prototyping circuits. What you do is you take some specially made very thin wire and a special tool with a hole in it. You insert the stripped end into the tool, and then you can put that over the terminal and twist the tool, and it wraps the stripped end of the wire very tightly round the terminal. And voila! Soldered the wire wrap wires onto a piece of strip board so that I could easily connect them to some bigger wires which would come out of the back of the case. I nipped the spindle to length with top cutters. I programmed an Adafruit Trinket, put it on a breadboard and connected it up to the stepper motor, and then tested it out by twiddling a pot to see if the needle moved in the way I thought it should. Now I had to design the circuit. The tank sensor is basically a variable resistor that moves as a float on an end of an arm which connects to the resistor, moves up and down according to how much petrol there is in the tank. The circuit needs to measure the value of the resistance. The first way is to pass a constant current through the resistance, and then Ohm's law tells you that as the resistance varies, the voltage across the resistor will vary in a way that's proportional to the value of the resistance. Second way is to put the resistor in a potential divider. The output from this will not be linear. It will not be directly proportional to the change in value of the resistance. So that would seem to be a disadvantage. However, the tank sender resistance is itself non-linear in order to suit the characteristics of the original gauge. So I needed really to test to see which arrangement would be best. This is the constant current circuit. The LM317 is built to ensure a voltage of 1.25 volts between the adjust and the out terminal. So with the values shown, that means the output will always be 20 milliamps. This is the constant voltage circuit set at 6 volts. I connected up each circuit in turn. I moved the float up and down, measured its position with a ruler and measured the voltage for each particular position, and then plotted the results on a graph. The straight line represents the best result, as it means that the output voltage is directly proportional to the position of the float. Surprisingly, that was the constant voltage option. So that's what I'm using, and my circuit looks like this. The Trinket has 5 pins, which is just enough. 4 digital outputs for the motor and 1 analog input for the tank sender. PCB is easily designed on DesignSpark PCB software, which is free. Then the designs printed out and used to produce a photo etch type production. Now for the software. When power is turned on, the Trinket doesn't know exactly what position the stepper motor's in, so it takes it enough steps clockwise to make sure it's up against the stop to establish a fixed position. Then measures the voltage from the tank sender circuit 50 times, averages the result, and uses that to move the needle of the gauge into the initial position to register the contents of the tank. It then goes into the main program loop. This involves taking 500 readings every couple of milliseconds and averaging the results. I'm hoping that that will be enough to avoid errors due to slosh of petrol in the tank, but it may need more damping than that. The circuit fits quite neatly on the back of the instrument cluster. I checked the calibration by fitting the unit on the car and filling up the tank with measured quantities of petrol. Here's the finished item. Further details can be had from my website.